Hello, everyone. I am Howard Zhang from ARM. Today, my colleague Jian Yongwu and I will give you a presentation on secure container runtime on ARM. Here is the agenda for the first part. Firstly, I will talk something about normal container and why it is not secure. Then I will give you an introduction on gVisor and why gVisor is secure. Finally, I will talk something about gVisor on ARM64 and the further plans. So let's begin. Here is a normal container. You can see there are several layers of normal containers. It runs as unprivileged users, job capabilities, and C group for resource isolation, and C group used to limit account and isolate resource group like CPU set, device, and memory. Also, it uses namespace for name isolation. Its isolated network PID mount user IPC UTS. So normal container is a relatively isolated environment, but it is not secure enough. Here are some secure vulnerabilities that do harm to container. As you can see in the first bullet point, a single vulnerability could lead to privilege escalations or information leaks. Also, as network stack is shared across containers and hosts, a single malformed packet in container can crash host kernel. So the root cause is that host and container share the same host kernel and device driver. Containers are not good security isolation boundaries. There are only one layer of isolation which is provided by kernel. This means that a single bug in kernel may make all container compromised. Here, we provide two attempts to resolve this problem. One is gVisor. It is a user space kernel. And another one is Kata. It is a lightweight virtual machine. Let's begin with gVisor. gVisor is an open source container sandbox released by Google. As you can see, it provides a binary that packages all components of gVisor. It can integrate it into Kubernetes system, just like other OCI runtime. Here is where untrusted application running. As we know, user space application interact with kernel by doing system call. To avoid untrusted application touch kernel directly, gVisor put a platform syscall switcher here. The platform syscall switcher intercepts syscall from the application and pass them to the user space kernel with no further handling. It also do basic context switching and memory mapping. Here, we support two platforms. One is ptrace. It uses ptrace sysmu to trap syscalls. Another one is kvm. In this platform, gVisor serves as a VMM and guest OS. And this platform needs hardware virtualization support. This one is the core component of gVisor. It's called Sentry. It is a user space kernel. Each application instance has its own Sentry. The Sentry handles syscall, routing I/O to go first, and manages memory and CPU, all in user space. But Sentry cannot visit file directly. Instead, all file visiting jobs is done by gVisor, a process that specifically handles different types of I/O for Sentry. You may ask why gVisor put I/O in a separate process. It is just because many attacks arm to file access. By the way, the gVisor and Sentry communicate via 9P protocol. The last one is syscall filter. Via syscall filter, the Sentry and gVisor are allowed to make limited filtered syscall to the host OS. Okay, this is how gVisor looks like. Let's talk something about why gVisor is secure. Here are two effective ways to make environment more secure. 1. Increase isolation layers. 2. Reduce attack surface. gVisor manifests this principle as a multi-layer system. An application running in the sandbox interacts with the user space kernel. The sandbox mediates all interactions with the host OS and beyond. Also, platform syscall switcher provides strong isolation. Like when you're using KVM Pro platform, it's almost like a normal virtual machine which provides memory and virtual CPU isolation between untrusted application and host. Sentry is written in pure Go, and this making it less vulnerable to buffer overflow and related memory bugs that can lead to a variety of compromises, including code injection. It emulates Linux using only a minimal and audited set of host OS syscall. This limits the host OS attack surface exposed to the Sentry itself. To be more specific, there are around 350 syscall in Linux kernel. The Sentry has supported 258 most common used syscalls, and only 80 of the 258 syscall would pass to Linux kernel, while other syscall is handled in user space. The syscall restrictions are enforced by running the Sentry and gVisor with syscall filter, which enforces that Sentry and gVisor can only use expected set of syscalls. So the attack surface is greatly decreased. As we talked in the previous pages, all file I/O is required to go through gVisor. This preventing the opening or creation of file descriptions, eliminates whole categories of bugs around file permissions. In another word, hackers need to break Sentry, Sandbox, and gVisor. Then it can access other files on the host. The last one is network stack. gVisor implied a user space network stack in Sentry. It only uses up to 3 host OS syscall to read and write packet. This also decreases the attack surface. Okay, it is the introduction of gVisor. Let's take a look at the current status of gVisor on ARM64. 1.5 years ago, one of my colleagues gave you a presentation on gVisor on ARM64. In that presentation, he shows on ARM64, we can run a basic hello world in gVisor from ptrace platform. Now we have support both KVM platform and ptrace platform. All tests have passed, which include 230 syscall tests for KVM platform and 696 syscall tests for ptrace platform. Also, the general usage is fine. We test it while repeatedly compile kernel in gVisor. And also run various application benchmark in gVisor on ARM64, include Sysbench, Redis, FIO, TensorFlow, iPerf, NGIX, FFmpeg, and so forth. We also do some tunings on gVisor, like we apply bitmap to FD table. It improved 25% speed when create a large number of FD, like creating socket. We also fix the mmap cache error. It improved 100% speed when doing mmap in gVisor. Here is the further plan for gVisor. We will keep making tunings on gVisor, as there are still some performance gap between gVisor on ARM64 and ARM that on x86, especially in FIO. We also want to decrease the performance gap between gVisor and the normal container. The last one is user space network stack. Although it reduces the attack surface, but the performance of the user space network stack seems not so good. So we will do some investigation on it. We also want to apply some new features to gVisor. As the Sentry and Gopher communicate with 9P protocol. The performance of the 90P protocol seems not so good. We want to introduce VirtIO or IOU ring to replace it to get a better performance. Okay, here is all about gVisor. Let's welcome my colleague Jian Yong to talk something about Kata container.
Hello, I'm Jian Yong Wu from ARM. Now I will give you a talk about Kata container on ARM64. That's the agenda. First, I will show you what's Kata container. Then the highlighted part is the Kata container status on ARM64. I will show you some features enabled in ARM64. In the end, I will show you our next plan. What's Kata container? It is a secure container runtime based on lightweight virtual machine. This picture shows the Kata container architecture. The big box is a KVM virtual machine. So as Kata is a virtual machine, so its security can be ensured by the virtualization technology. In the end of, as the Kata has reduced the guest kernel and the system service, so this virtual machine can start very fast. Inside the virtual machine, an agent can be the first process, and it can start containers. The applications will be run in the containers. This the container DStream Kata v2 will be the Kata binary. It can communicate with the agent inside the VM. And as the Kata is OCI compatible, so the container DStream Kata v2 can be stored by Kubernetes CLI. That's Kata container. So let's show you something about Kata container status on ARM64. As UEFI and ACPI has enabled in Kata on ARM64, you can use it by set the UEFI image path to pflash in the Kata container configuration. Use UEFI, the memory hot plug is available, but you will get extra latency. If you doesn't use hot plug features, you can start Kata without UEFI. You just need to comment out the pflash term in the configuration. Then you will get better performance in startup time, but you will have no ACPI features. The memory hot plug is enabled on ARM64. This memory hot plug will be based on ACPI. Thanks to the upgrade the guest kernel to 5.10, and thanks Yuanzhe in community to twist memory 8 strategy in QEMU. So you can try memory hot plug as the following steps. For now, there are 3 VMMs support in Kata on ARM64. This chart shows you the support features status for these 3 VMMs. Now we can see, except CPU hot plug, lots of features has enabled in QEMU, but there are more something we should to improve for Cloud Divisor and Firecracker. The KVM PDP clock is used for time sync between host and the VM in a high precision. This new feature has emerged in the latest kernel. Now we have ported this code to the guest kernel for Kata on ARM64. Now I will show you the next plan in Kata on ARM64. As the CPU hot plug is a key feature in Kata container, so it is important to enable it. After also feature enablement work, we will do some performance tests and performance tuning. Early this year, ARM v9 CCA is released, and it is a feature for confidential compute. It can be used in Kata to enhance its security. Now, we are waiting for its ready in hardware and software. At the end of this talk, I will show you the comparison between RunC, Kata, and gVisor. From this chart, we can see that the RunC has the best performance except security. As to Kata and gVisor, the gVisor is better for startup time and memory footprint, but is worse at I/O performance and software compatibility. That's all. Thank you.